Okay, guys. Oh, right. Okay. What's the responsibility of a file manager?
Monitor resources.
Monitors the resources. Okay, monitors all the files. Good. Give me another responsibility of a file manager. It follows a policy, a predetermined policy. Allocates and deallocates files. Very good. What about the device manager? What are the responsibilities of a device manager? Any idea? Okay. Anybody was here last week? Give me a responsibility of a device manager. Monitors all devices. See, guys, it's the same responsibilities for all the managers we have about 4 or 5 managers. They pretty much do the same thing with the things they manage. So the device manager keeps an eye on all devices. The file manager keeps an eye on all files. But the CPU manager, the processor manager, what does it do? What does it keep an eye on?
Deallocate.
What? The devices?
No.
The files? Memory?
Everything from the computer.
No, I'm talking about one manager, not the operating system. The processor manager, what does it do?
Monitoring the stack, the memory stack.
It monitors the memory and the devices. Yeah? No. What does the processor manager do? Allocates what?
Processor.
The processor, the CPU. That's the CPU. Okay, so every manager manages something. The processor manager manages the processor. What does it do? It keeps an eye on the processor. Is it busy or is somebody's using it? And if somebody wants to use it, it will allocate it and it will take it back. We say deallocate. And this goes the same for all resources. All group of resources, they have one manager that looks after them. So if you are asked what's the responsibility of, say, the devices manager, okay, give me what responsibility a device manager does. What does it do? Okay. He will tell you. What does the device manager do? Okay, guys, listen to me. In the old days, we used to say, leave the mobile phone. But now I can't tell you to leave it. Maybe you're following up through the lecture with it. So, but listen to me. Try to, maybe while you're doing something, also listen. Like I'm asking these so you'd remember, so you won't have to sit down and study them at home for too much. Okay. Why do we need an operating system, guys? Out at the very back there, my friend up there. Yes. What's really the purpose of having an operating system? Why do we have an operating system on computers? Yeah? Any idea? Why?
To manage the hardware.
To manage the hardware, the software. Yeah. To manage all resources. And what do we mean by manage them? That means use them in the best possible way. That's the most efficient way. That's the main purpose of an operating system, is to use the resources in the most efficient manner and give the best results possible. Okay, I need to study this more. I need to ask more questions, guys, just to keep you up to date with this stuff. I need you to know this stuff like that, like quick, so to go further, you need to understand these basic things. And that's the reason why I'm asking. So we started looking at those notes yesterday. We said that an operating system consists of a number of managers. They are the device manager, the processor manager, memory manager, file manager. Nowadays they have communications manager. And operating system is broken into smaller systems called subsystems. And we call them managers. They are known as the managers for specific tasks. So every manager manages something. And but they all do pretty much the same thing with whatever they manage. So every manager will monitor the resource it's responsible for. So if we say file manager, it will monitor files. What do we mean by monitor? Keep an eye on them. Are they available? Are they busy? Is someone using them? Who is using them? Are they entitled to use them? Can we use them better? Is there someone else that wants to use them? That's what we mean by monitor. Where are they at the moment? And so on. So depending on the resource, some resources slightly, they have specific tasks. And then if they need to be used or allocated or deallocated, we do that based on certain predefined policies. So somebody makes a policy. For example, two processes want a printer. Who would we give it to? The operating system will just follow what we want it to do. So it needs a policy. We make the policy. The manager system administrator will say, we'll give it to the smaller process maybe, or give it to the higher priority process first. That's what we mean by a policy. So that's it. The operating manager or the operating system, that particular manager will follow this policy. And if we change the policy, then it will follow that as well. So any manager, if you're asked, what's the responsibility of a device manager or file manager or whatever, these are the main responsibilities. It will monitor the files, if it's the file manager, or you say it will monitor all the devices, if you're talking about the device manager. It will follow policies set up by the system administrator, and it will also do the main two jobs for the operating system. Each manager will allocate. That means a process says, I need memory, we'll give it memory. That's the memory manager will give it. If a process says, I need a device, I need a printer, it will be allocated the printer. And it will have it until the manager decides to take it away from it. Not until it's finished. Until it's time for the processor manager, or sorry, the device, whichever manager decides, okay, that's enough. I'm taking the printer away, or I'm taking the CPU away from you, or I'm taking the file, or I'll leave it with you. So so we call this operation deallocation. Right. What's the difference between a program and a process? Any idea? Any idea? What's a process and what's a program?
Process is complex of programs. I mean, program is group of process.
No, one program and one process. They're pretty much the same. Sometimes we say it's a program, sometimes we say it's a process. What's the difference?
Once you have written the program, after that it's a process.
What do you mean after that? After we delete it?
Process comes after programming. What we perform is for
Say again?
After we design program, after that what we perform is called process.
No, not really. Okay.
Program sets of instructions like processes and
Exactly. Processes are programs. Say a program we start calling it a process. Why? A program in execution is a process. I told you this last week, but it's okay. I'll tell you again. Well, I'll ask next week, and if you don't know it, I'll tell you again. So you write a program. A program is a list of, what's a program first? It's a list of commands or instructions to do something, hopefully something useful. Or we can have useless programs as well. but it's sitting on the hard disk, it's stored, doing nothing. Like maybe a book that has instructions how to cook a meal. Instructions, but they're sitting in the library on a shelf doing nothing. That's a program. But once you take it and you start implementing it, executing it, then we call it a process. Okay, so a process is same as a program, but it's a program in execution. When it finishes execution, that's it, the process is done. It goes back, you know, we have a copy of that program. So a file on the hard disk never say about it a process. It's a program stored onto the hard disk, doing nothing, idle, static. But if you want to execute that program, you need to bring it into memory. You put it into memory and we start running and we call it a process. Don't call it a program. Again, while it's executed. Right, so we'll get used to those terminology. I'm just, every opportunity I get, I push it and see until hopefully you'll be speaking professionally. Okay, allocate and deallocate. That's given the process or the program whatever it needs of the resource. When a program says I need to run, execute, when you double click on any icon, that's just a request to the operating system. You say I want to execute this program. The operating manager will say, right, you want to run the program, then you're going to need memory. I'll call the memory manager. So I'll call the memory manager and say, this program wants to run. So the memory manager is going to find space of memory enough to fit the program and will allocate it in its own record and say, I've given this memory to this program. Every program will have an ID while it's running. Every program, when it starts running, becomes a process, it'll have an ID, a number. Just like every student that comes into college, we give them an ID, just in case two students have same names, or just in case a student is to be dismissed off college, we don't dismiss the wrong student, so an ID is important. Every implementation, every program you write, if you need to do something with multiple items, you need to identify them. And the best way to identify anything, books in a library, or patients in a hospital, or medicines in a pharmacy, or whatever it is, students in a college, or staff members in an organization, go for numbers, start numbering them. Because hopefully, everybody, they get a number, and you start dealing with that number, just in case they are similar in date of birth, or similar in names, or similarity in nationality. But numbers, make sure they're unique numbers, and that becomes your ID. And this is used everywhere. It doesn't matter what it is. In every factory, in every organization, every company, there's always this uniqueness. So anyway, that's the story. That's what happens with a program that needs to be executed. The request comes into the operating system. The operating system says, in order to run this program, we need memory, so it's called the memory manager. It will need some CPU time, we call the CPU manager or processor manager. And the processor manager will look and say, okay, start executing. We'll ask maybe for a device, needs a file. So the request goes to the file manager. Remember, you can never, no program or user can directly deal with anything. You cannot open a file and read it on your own, or your program does it. You cannot delete a file. You cannot go to the printer and start printing. Every one of these commands has to go to the operating system, to the appropriate department of the operating system. Whether it's memory, goes to the memory manager, device goes to the device manager, and so on. Because, as you can see here, the operating system kind of surrounds this thing in the center, and that's the hardware. So imagine all the hardware, memory, hard disks, tapes, anything. Everything is in there. And this is us as users. And the users are either programs or people. These are the users. You are either sitting at your keyboard and you want to do something. In this case, you are the user. Even for you to talk to the operating system, you will also need a small program. Because without these little programs, you might have to type 100 commands just to do one thing. But somebody has already written those 100 commands in a small program, and you just call them. So if you are a user, you use one of these programs that talk to the operating system will handle the hardware on your behalf. Will deal with your request. It's either accepted or refused or whatever. So as you can see here, there's no way of reaching the hardware directly. And now people, some people specialize in programming in this area, called system programming. If you are programming around in the outside here, and or an application programmer. And the user here can be a person sitting at the keyboard, or it can be another program. Sometimes you write a database program, some programs that, or even a simple program that adds two numbers together. But that program, before it runs, and it needs to print something, it'll ask somebody to type in a number. You can't go and print something on the screen without asking the operating system. So your program will talk to another program, or talk to the operating system, and say, display this statement on the screen, and then ask the user to type in. So read something off the keyboard. So you can't really read from the keyboard without asking the operating system to do that on your behalf. And for example, if you say, right, I'm going to put 0 in X in memory, when your program is running, and it puts some value in memory, it has to go through the memory manager. Any idea why? If the memory manager has allocated your space, he said, here's the space for you, from location 0 to location 5000. And you are sitting in location 2000, you say, put 0 in this space. You can't even do that without asking the operating system. Why? Anybody knows why? Okay, I mentioned it again last week, because every time you want to change memory, the memory manager want to make sure that you are allowed to do that, and you're changing the space that's allocated to you. You can't go to another part of memory and start changing it. Another part that belongs to another program, or another part that belongs to the operating system. So all these things the operating system does for many reasons. One of them is making sure that no program will rule or ruin and destroy other programs or mess them up. That's what some bad programs do that are viruses or similar, that they start running, but they go somewhere else in memory and they start changing it. They shouldn't, but sometimes they do fool the operating systems. But the operating system tries to, once it gives you space in memory, it will not allow you to touch any other space in memory. And that's another reason why nobody is allowed to touch nothing, because a printer can be used to print something for another user. We don't want you to come in and stick in a few images in that report when they take it out. So the device manager will not allow you to go near the printer when it's being used by someone else. It's for not just for control and efficient use, but also for making sure there's no abuse for these resources, or there's no destruction. Sometimes people will go in and say, delete all the files in a company. Like if you delete all the files on a server, it can be serious. That's why the file manager will not allow you to go and do any command except through the file manager. And when you say delete this file, the file manager will make sure that you have the right to delete it. It will not allow any delete command to be executed without security check. So these are the different reasons why an operating system is needed. It's for as it started, let's get things done in the most efficient, the best way possible, the cheapest way and the most efficient, and the least energy, and the fastest, all these things. But then also for security reasons as well, for good control. So then we mentioned this, so we have the different managers. The first one, this one is called the memory manager. So it's responsible for all memory, main memory here. We're talking about main memory. And main memory is so important that it's required. Any program that needs to execute or run, it must be located in memory. You cannot run a program while sitting on the hard disk. Executing a program, the instructions of a program is like, something similar, but not the same. But if I say, okay, can you do this calculation, and you don't know how to do it, you don't have a clue. So what you do, you go to a library, get a book that shows how to do it, read it in, that's transfer the information to your main memory, to your brain, and then you can execute that problem or solve that problem. It's like if you, in a restaurant or a chef in a kitchen, if they're asked, cook this meal, but they've never seen this meal, they don't know nothing how to do it, they can't do it. In order to do it, they must bring the instructions from a book or somewhere that's sitting in a library and bring it into their mind, and now they can execute it. The same with programs, computer programs. In order to run a computer program, you must go to the hard disk, pick that program, put it in your memory, now you can execute it. So every program or a process, in order to execute the instructions for that program, need to be uploaded into main memory. So that's how important it is, main memory. You cannot run a program if you don't have main memory, if you cannot bring that program into main memory. So, and main memory has historically been very expensive, very complicated to manufacture, and there's very little of it over the history. And there has never been enough memory, right up until now. Every time, even technologically, you can have more memory. Actually, we have bigger programs and we need even more. We have bigger memory, then we need more memory. And operating systems are getting bigger, and our programs are getting bigger, and our games and graphics and everything needs more memory. So memory is very important to run programs, and there's always very little of it, not enough for all programs. And so we need to be very efficient with use of memory, and that's the responsibility of a memory manager, is to preserve the space in main memory occupied by the operating system. First thing, when a computer starts, first programs we upload are the operating systems. So operating systems needs to be in main memory. So, and that's one responsibility of the file manager, to make sure that this part of memory that belongs to the operating system, it's allocated to the operating system, and no other program should go near it. That's for certain. So, and that still goes for all computers. Anything that's computer kind of oriented, like mobile phones, they're computers. They have CPU, they have main memory, they're just mini computers. Or mainframe, whatever computer, it'll have memory. And the first and most important part of that memory is the part that's allocated to the operating system. Now that's the one that manages the entire system. And nobody should go, no other program. That's what viruses always try to do. And programmers who program or write malicious kind of code or programs that do damage or take control over a machine or something like that, is they try to get into the operating system part of memory. But when the operating system, once it takes over, it makes sure nobody goes near the main memory, near that part that belongs to the operating system in main memory. And then also the memory manager, every time somebody comes up and say, do this to memory, or give me this memory, or clear this memory, that this command is a valid command. So the memory manager checks every command that it's a proper command. Why? If you say change location 5230 in memory, change it, put any value on it, it checks, are you allowed to change that? Does that memory belong to you, or does it belong to another program? Or maybe it belongs to the operating system. This check is done every time. you say x equals 7, or 5 plus 5, c equals 5 plus 5. I mean, put 5 plus 5, put the value, the result in c. C is just a place in memory. So the memory manager will check, is there a place in memory where you want to put any value? Are you allowed to put that value in? If it's a memory that's allocated to you, it will execute it. It will say, okay. If not, it will terminate your program. Your program will be terminated for violation of memory. They'll probably write a log, a note in the log. So maybe the system administrator will say, oh, that program is trying to access other programs' memory. Maybe it's a virus, so then it can be checked and removed. So memory manager, memory is so important, and protecting it is also important, and that's the responsibility of memory manager. And sets up a table. So all memory managers will have a table that says which program is running where in memory. Addresses from location 0 to 2000, it's program number 1. From 2001 to 6000, it's another program, and so on. So it knows. So if a program says change this memory address, it'll go to the table and say, oh, your program number 5 goes to number 5. What memory space you have? This space is the thing you're going to do inside your space. Yeah, okay, do it. So it will be done. But every command you send that changes memory or modifies memory or goes through the memory manager. And it allocates and deallocates. So that's the main responsibility again if a program needs memory, it's the memory manager that decides, okay, here's the memory space for you, and it's put there. And usually, if you upload a program, usually into memory, all the instructions go there and they stay there, they never move. Even though the program is moved to another queue, goes to the printer, waits for printing to finish and all that, but the code stays in the same location. The processor manager looks after the CPU. And obviously, in most computers, there's only one CPU or one main CPU. Sometimes you have a second CPU. It's called math coprocessor, but it's only a CPU to do mathematics instructions or graphical instructions. But most computers, they have one main CPU. And that CPU will execute all the programs. And again, CPU is very, very complicated and expensive, probably the most expensive part of a computer. And it's the most complex part. And the CPU is the one that actually executes the instructions, executes all programs. I remember there's only 512 instructions altogether that the CPU can do. But those 512 instructions are the ones that do all the analysis and all the programming and all the games, and everything is done through the very basic instructions. But also, CPU is so important that it's the one that actually does the work. And if you have 10 programs trying to run, they're all kind of competing for the CPU time. They're also competing for memory, but okay, hopefully each of them got enough memory to run, otherwise they wouldn't run anyway. So in the older days especially, you couldn't run a program if it was too big, because the whole program has to be put in memory. If your program is bigger than memory, forget about it, you can't execute it. That's why in 20 years ago, 40 years ago, you have to write a program that works, but it has to be small as well. And still now, the pressure is still on for smaller programs, but not as much as it used to be, because they found other ways now that we don't have to get the full program into memory, chop it, get some part of the program, put it in memory, start executing it. If you need the other part, stop, swap, bring another part, and we'll talk about this later on in memory management. But overall, you need to have the program in memory, and the CPU can only execute. How many instructions does the CPU execute at any given moment of time? Anybody knows? How many instructions can the CPU execute? Not in a second, just how many in one moment of time? Millions? A million? No, every second it can execute a million instructions. But on 1 millionth of a second, how many instructions can it execute? One. A CPU can only execute one instruction. So if you have 5 programs running, they're all running simultaneously, it doesn't mean they're all executing in parallel. That's not the case. No CPU can execute 5 instructions, unless if you have 5 CPUs. If you have many CPUs, then every CPU can execute one instruction of one program. Remember, a program can have 50,000 lines. When it's compiled, it probably gives 200,000 instructions. And maybe all the instructions can be executed in 1 second, but any moment, the CPU is looking at one instruction. It says, take whatever, in memory location, on this location, and add them together. So it's doing that. And it does nothing in millionth of a second. But while it's doing that, it's not doing anything else. So if the CPU is running execution of this instructions from this program, and the other program says, I'm running as well, they're not really running. In reality, there's only one program that's being executed. But how come then we can have 10 programs running? Remember the nature of programs, how programs run, how much CPU they need. Every program, you know this, I told you before, every program starts running, executing, and the program by itself, most programs will have to stop and say, I don't want the CPU. Why? Any idea why? What does a program want if it doesn't want the CPU? Memory. That's already in memory. No, it needs something else. I can't hear you. It needs input or output. Every program must stop and say, I need to read information, either from a keyboard or from a file or from an incoming line. If a program doesn't stop and ask for information, it's a useless program. That means it's a program that will do the same thing all the time. Like if you have a program that just prints a list of numbers from 1 to 100, you run it again, it'll do the same thing. You run it again, it's the same thing. It's a useless program. It will be repeating itself if it doesn't ask for information. If a program asks for input, it has to ask for an input, or else it's a useless program. If it asks for input, then it will be what we call a useful program. It will say, right, give me some numbers. You want me to add numbers? Okay, type in 2 numbers. So it will stop, wait for you to type the 2 numbers, and here's the sum, for example. So it will always give you the sum of any numbers that you type. It's not the same execution, it's different. If you write a program and say, okay, you already give the numbers in the program and say, x equals 3, y equals 5. Please print x plus y. Please print 8. If you run it again, print 8. Run it again, print 8. But if you say, ask the user, type in a number, first number, type in another number, give you a different number, add them, and then every time the program runs, it will produce something different. That's a useful program. That's how all other programs should work. So the point I'm trying to make, every program in the world that's written, that's useful, it has to stop. It doesn't always say run with CPU until I'm finished. No, it doesn't happen that way. It says run, and then stop. Give me input. Whatever the input is. It could be open the student's file and read me the student record. Or get me the exam marks. Or give me the prices in a supermarket or something like whatever it is. So it has to stop and ask for information. If it doesn't, it's a useless program. So just always keep that in mind, that every program must ask for input and also must produce something and send it to an output. This input, where it takes it from, or this output, where it sends it to, are resources, devices. It has to go through the device manager. You can't just read by yourself from a file. You need a file manager to do it. You can't read from a keyboard. You need the device manager to do it. You can't print to a printer. You need the device manager. So the point is, and while you're reading, while we're waiting for input, or sending something to be printed or sent to a file, we don't need the CPU. The program does not need the CPU for that. period of time while it's waiting for input or waiting for output to be sent. So that's the time when we take, if a program says, okay, I need, get me some information from a file. The operating system says, go to sleep. You're already asleep, but the operating system says, go to sleep. So it puts that program to sleep and send a request to the file manager and say, can you please read us this information? Well, that program's asleep, it doesn't know, it doesn't need CPU. We take the CPU, we give it to the next program. Well, the next program starts running. And after a few millionths of a second, it will say, I need information from the keyboard. So boom, go to sleep. And we send the request to the keyboard, to the device manager, to check it and display information to the screen and wait for the input. So now we have two programs sleeping. The other program will sleep, we say, here's the CPU. And also the program will need something. So we have now the CPU. We go back to the first program. If it's finished, the input, we'll say, okay, wake up, here's the CPU and go. If its input has not been produced yet, we leave it. We go back and we keep going around these programs. So that's why we say we can run multiple programs, but what I want you to remember is that CPU can only run one program. The others are asleep. They're waiting for something, but that's part of their execution. That's how things work on computers. You get the CPU for a few little moments, and then you have to stop waiting for input or output, and during that time you give the CPU to the next program and next program. So that's what the CPU manager does, the processor manager. That's its responsibility. Go around these programs that need the CPU and check who needs the CPU. There you are. So, and if you find two programs waiting for a CPU, who do you give it to? This program or that program? What do you think? If there are two processes that are now waiting for a CPU, CPU became available. There are only two processes, process A, process B. Which one would you give it to? Any idea? Okay, yeah. So it depends on the policy. Whatever the administrator decided, it says, give it to the first one who asked for it first. Well, then you go to the first come, first serve. And if it says give it to the higher priority, then we must go for the higher priority one. But this guy came first, but it's not important. This one is more important. We give it to this one, and so on. And sometimes you give it to the smaller program. Why? Because if smaller programs finish out of the way, we'll improve our average turnaround time. Do we know what the turnaround time is? Any idea? You know what the turnaround time is? One at a time, yeah?
Time from initial beginning to the.
Hold on. Kamosh. Listen to his answer. Yeah, it's the total time, what?
From initial beginning to the final end of the process.
Exactly. So turnaround time for a program, from the first time that you double click on that icon, say start executing this program, of course that program will run, CPU will go to sleep, go to eat, get input, go out, eventually it will finish. It's not all this time, it's not all executing CPU. Part of it is going waiting, they call it waiting, I call it sleeping, but it's waiting for an input, and then gets the CPU, send something to an output, wait until it's printed, and so on. And then eventually when the program finishes, that moment of time, from the moment you started it, that's called turnaround time. And we try to minimize that turnaround time, or at least try to minimize the average turnaround time. And when the processor manager, in fact, the manager actually splits itself into two jobs. One is for handling new processes coming in, and one for dealing with the ones that are already in the system. It's like, for example, in a college, we have two systems. One that goes and recruits or gets new students arriving, they just arrive, get them an ID, get them something, get them settled. That's it, finished their job. Now you start attending classes that are looked after by another group, by another office. So same with the CPU manager. First, it deals with the new jobs that come in. So every time you double click, they call it the high level manager, the CPU manager. It deals with it, checks what kind of a program are you, how big are you, what priority do you have, and checks you, finds memory for you, so it gives you memory, calls the memory manager, of course, gives you memory, and checks, do you need any files? Talk to the file manager and say, this guy needs 6 files during execution. You might say, yeah, okay, no problem. And now once everything is ready, and they give you a process ID number, now you just came into the system, so they give you a number, and then they put you into a queue. And say, there you are, now it's time to wait for the CPU with the rest of the program. Now you're in the system. So that's the initial kind of manager. So you need to handle the jobs as they enter the system, and they call these schedulers, these programs that deal with jobs. They call them job schedulers or schedulers. That means they put you into a timeline. You start waiting for the CPU with a group of others. So you're gonna be like timetable. They give you a timetable, you join the queue and you start working. But they call these job schedulers. Job is like a program just arriving. It's not a process yet. It just came in, a program comes in, request, we give it memory, we allocate it maybe some resources, and we give it a priority, we give it a number, and they actually create a small card for it. And they stick it there, it's a label that now the system knows you through this label. What time did you come in? And they start writing this information as you go in. It's just like a student coming in, attending, got sick one day, we write it down, done an exam, we write the mark. And that's what happens to a program with the operating system. There is something called a process control block, like a label. You start, they put down your label, your location, where did we put you in memory? They write down where you are in memory, and how much. If you open a file, yeah, this file has been opened for it. Have you started reading? Yeah, it's right. Now at the moment it's reading record number 12 in that file. So they follow the progress of the file in something called the process control block. And then the other part of the processor manager is called the process scheduler. So we have 2 schedulers, the job scheduler and the process scheduler. The job scheduler is the one that handles the newly arriving requests for execution. The process scheduler is the one that already the job is in the system. It's following, it's being looked after by this person or this part that we call the process scheduler. So if you're asked, what's the difference between a job scheduler and a process scheduler? They're just smaller parts of the processor manager. And the processor manager is part of the operating system. So as you can see the hierarchy, we have an operating system like the Prime Minister, right? He is now Minister for Health. That's like the processor manager. Maybe the Minister for Health has 2 parts, a hospital and maybe outpatient, whatever it is. So here we have 2 parts that they both make up the processor manager. One handles the new jobs, they call it job scheduler, and one that deals with the processes in the system, and they call the process scheduler. We'll see later on, their jobs are a lot more interesting and easy to follow. Right, device manager looks after all the devices and does the allocation and deallocation. And with the processor manager, there's also the allocation. Finally, you allocate the CPU to some process and deallocate it.
Is this the same manager when you open Android Studio, device manager, and this device manager?
Is it the same with what?
When you open Android Studio, there is device manager. You can manage your SDKs, I mean the emulators. Or is this different one?
I didn't quite get the question, but let me answer and see if this answer goes towards your question. Whether this is on Windows operating system or Apple operating system or any other operating system, they have a device manager that does the same job. They have a CPU manager or processor manager that does the same job. Does that answer your question?
Yeah, so there might be many device managers. More than one.
In the operating system, in one operating system, there's one device manager. Every operating system has one CPU manager of the CPU, and sometimes there are many CPUs. They still have one CPU manager, might have a smaller part underneath it that manage that CPU for me. So, but with the device manager, there's one device manager. And memory manager, there's one memory manager as well. Okay, so the operating system with network capabilities, they started introducing network managers to help manage the network. So the machine hardware, we've already if you've done the hardware, then you'd have some idea. Otherwise, you'll do the course next semester. So the main hardware that the operating system looks after, it looks after memory. There'll be memory chips. It will look after or manages input and output devices. Every device connected to the computer is considered an input or an output device. It can be a scanner, or it can be a printer, or whatever other hardware, hard disks, storage devices, anything attached to the computer is considered an input or an output device. A camera is also an input device. The communication line, internet and all that. Storage devices and CPU, they need to be managed. This is the hardware that needs to be managed by the operating system. Why is it you need to communicate with everybody? Do all your communication and finish it and listen to me. Or if you need to communicate, guys, if you want to talk, you can step outside, do all the talking and come back in anytime. And maybe ideally if you use the back door. There's another door there in the lecture room. Okay, so here are examples of the hardware. This is the CPU here, maybe. Okay, here's the front door. So a monitor is an output device. That information can be sent there, messages printed or pictures displayed. Keyboards and mouse are input devices, and all these devices here, either, what's that, disk drive, interface, modems, parallel printers, USB, scanners, cameras, everything. So all these are input-output devices. If they're available, they'll be managed. Now, how does the operating system know how to use all these devices? Like imagine if you had a hard disk that was manufactured by some company. Whatever the hard disk is there a hard disk shown? That's an optical drive. Let's say somebody changed this optical drive, brought another optical drive manufactured by a completely different company that you can store information on, but it uses different instructions. How does the operating system now knows how to write onto this new device? Because, guys, the operating system has this software that we said it puts it in main memory, but also checks all the devices. The operating system doesn't know how to read from this keyboard, or from the mouse, or from camera, or doesn't know. When you say store this, write this information to the hard disk, you need, for every hardware, you need special command to write the information. You can't just and even if it's a hard disk, you replace it with another hard disk manufactured in China or in Canada, they'll be completely different. The instructions to write to this hard disk is different. And maybe this hard disk has 2 surfaces to write on, this one has 16 surfaces. So every time a device is connected to the computer, the operating system will look at it and say, oh, that's a new device, that's different. Now, where is the software drive, the device driver for that device? The device driver is software that comes from the manufacturer. So if you have a factory that makes a new printer, so the command to print a line on this printer is different to any other printer. So you write, okay, if you want to print a line, here's the procedure or function of the commands that you must issue. So this comes from the manufacturer. And most of the time they're standardized. So the name of the command, print a line, is the same. But how do you actually print it is different from one printer to another. So if we get a new printer, whether it's laser printer or dot printer or whatever, the command will come from the software, from the manufacturer. So when the operating system finds a new printer, you say, okay, where's the programs to print onto that printer? Where's the function? So we get that, and we call that device driver. So every device that you buy, there's some software that comes with it. And it's absolutely important. It's called the device driver. That comes from the manufacturer. And you need to install it. When we say install, that's what we do. The operating system says, okay, where's that software for this device? Where's the device driver for this printer? Put it in the CD-ROM or put it in USB, and the operating system goes, takes it, and puts it and becomes part of the operating system for that device. So now if you say, print a line on this printer, the operating system, of course, the device manager will say, oh, that printer, I have, this is the device. So we call that function, say, print this information to that printer. So that program that was made by the manufacturer is used. It becomes part of the operating system. So that's how, like, if you remove this and get a laser printer then after that, then it will have the software. And the software that's made from the manufacturer, you put it there, it becomes part of the operating system, as long as that printer is there. So this is how actually operating systems can use any device, any keyboard, any scanner, anything you think of, you think, wow, the operating system, how could it know all these? There must be thousands of types of printers, hundreds or thousands of different types of hard disks. How does it know? It doesn't know them all, it knows none of them. But anytime you put a device onto your computer, you'll say, where's that driver for that? And you have to have the driver or else it will not be used. But so what they started doing now in the world, they started standardizing the commands, making the commands, for example, to a hard disk, to a file. To a file, there are only 5 or 6 commands worldwide. How to open a file, create a file, open a file, write to a file, read from a file, close a file, delete a file, maybe rename a file, 7 commands. The file manager doesn't know how to do any of these, but it will get the software required to do each one of them, and it keeps it. So anytime your program says, open this file for me, well, the file manager doesn't know how to open it, but it has the required command that came from the manufacturer to say, open this file. So now they became standard, almost. So you don't even, possibly you don't need they say, listen, our commands to use this keyboard is the same as the international standard command. There it is. So you don't even you don't need that software from that manufacturer. The manufacturer accommodated their device to use this standard software. So sometimes you don't even need, but for complicated devices, for new devices, yeah, you definitely need the software from the manufacturer. But mostly from keyboards, they became so used, so we know exactly every key and they're being standardized. So sometimes you don't even need the software from the hardware. But if you have a new device, keyboard, that uses the wireless and it's kind of, it's a little bit not usual, not the default, then you need that software that comes with it and store it or install it onto your device. Okay, so a lot of this stuff you probably already know. Some of this stuff is new, but I'm solidifying the ideas, how things are built, how do they work. So when later on we start talking, it all starts making sense. Right, okay. Machines. the hardware itself. Computers. What are the different types of computers? And the first one, and the oldest one, the first computer they made was such a big computer that has one CPU, and it has many users. The CPU was so expensive, it used to cost over $1 million to buy that computer, $1 million. But so it's an expensive computer that has one CPU and has many users, maybe 100 users that can reach in, and every one of them put in their program, and you can have 100 programs executing at the same time by one CPU. And people used to log in with a keyboard and a monitor, and there's no CPU in their monitor or keyboard. So there's one CPU, one big computer, one big processor, and everybody is attached to that through what they call dumb terminals. Dumb terminals, that means terminals that have no intelligence, have no CPU. Anytime we talk about intelligence, we mean CPU. Who is taking care of the time? Who is our timekeeper? Is it you? You're lost, aren't you? Okay, what time are we supposed to finish, and what time is it now? 1 o'clock. Okay. I started seeing people getting itchy and sleepy. And okay. So guys, if you ask, what's a mainframe? It's probably one of the first computers that was manufactured. And it's a multi-user. You need to say, any type of computer, you say, is one user or multiple users. Mainframe is multiple users. Still, we can run, even now, mainframe today, hundreds of users. They use the same machine. It has a powerful CPU, always powerful, relatively. 50 years ago, still the most powerful. And even today, it will be the most powerful CPU. And there'll be many, many users using it, but the mainframe actually was used back in the 60s. And there it is, the IBM 360 Model 30 was one of the biggest kind of mainframes of the time. It actually did cost $200,000 at the time to have that computer. And many users can use it, and it actually needed an 18 square feet, that computer, right? And it uses these valves that act as memory cells that generate a lot of heat and use a lot of power, electric power, but it needed actually cooling systems to cool it down. So since late 60s, they invented transistors. The transistors just reduced the technology, the size of actual memory cells, and reduce the power it consumes. So you can have thousands and then millions of switches in such a small space. This is due to the invention of transistors. So transistors what really transformed computers from that inefficient, high power consuming device into a small device. And not just computers, radios also turned, recorders, everything, all electric equipment suddenly reduced in size by the introduction of transistors. But mainframes were actually before transistors were introduced. So they were large machines that had large volume, and they used a lot of electric power, and they produced a lot of heat, and they needed cooling down. But they had powerful, at the time, processing power, and it supports multiple users. Then in the 70s, 70s, they reduced the size of this mainframe with the introduction of transistors and improvement in technologies. And they had something called the mini computer. So instead of the mainframe was very, very large computer, wasn't really very efficient, but into the 80s, they produced something called the mini computer. It's the same idea as a mainframe, but of course, with much improved technology, much improved processing power. And now every workstation, remember the dumb station that they only had a keyboard and a screen, now they had a keyboard and screen and a processor. So the stations that connect to the main computer, they had their own CPUs. So that's like what we have today. They're like a big desktop sitting, it has its own CPU, its own memory, but it's also connected to another main computer, a server, you might call it a server nowadays, that has also a CPU that has a lot of memory, a lot of power in it as well. So, and they call this the mini computer. So the mini computer is a smaller version of the microcomputer. It's a lot cheaper. It only costs about $20,000 or $18,000 as opposed to $200,000. Remember, mainframe costs $200,000. Mini computer, this is 20 years later, it's reduced to $20,000 and it worked a whole lot better. Every station had its own CPU. All the computers are connected, but still to one machine. And that machine possibly used much bigger applications that maybe couldn't support, each individual machine can support them all. So they had one big machine with big hard disks and some processing power that maybe they started using AutoCAD and those applications that need a lot of power. So you have only one version and every machine can download it and use it. But every machine has its own CPU. They don't all depend on the CPU of that server. So that's a mini computer. So it's an increase in power, increase in processing capabilities, reducing price and power consumption. And so it's improvement, a big improvement. A supercomputer are computers that have multiple CPUs. So nowadays, like a mainframe, but not just one CPU, it has 4 or 8 or 16 or 32 or 64 CPUs. Not very many countries have them. Very few countries in the world nowadays have a supercomputer. They can actually, imagine, instead of having one major CPU, you have 32 or 64 of them. You can actually process. And remember, on one CPU, you can run maybe 100 programs. Now with 32 or 64 of them, you have huge processing power that you can do programs, run programs that normally a normal computer might take 2 years to execute. They can execute it in 2 minutes. France has one, America has one, Britain, I don't know what other countries, maybe India has developed, yeah, a supercomputer. So supercomputers, okay, technologies, they are a bit more complex, but still they're made up of, standard CPUs, but there's a large number of them. So they can execute trillions of instructions per second. Microcomputer is the personal computer. It's that computer that you have with you. It's like a laptop. This started back in the 70s. Yeah, in the 70s when the first microcomputer came. That's the first computer that they call a personal computer that came under 1,000 euros, so $1,000 at the time. So as you can see, the prices went down from 200,000 back in the 60s to 20,000 with the mini computer to 1,000 in the 70s for the personal computer. But the personal computer, how many users can use it? Only one user. You can't connect multiple computers to one personal computer. The mini computer that costs around 20,000, probably also allows 20 users. The mainframe allowed maybe 200 users. Yeah, the mainframe is the bigger one. The older one CPU, and you can have 200 users who don't have CPUs. The mini computer costs about 20,000, maybe allows 20 users, but it's a lot more powerful in processing power. And every one of them has their own also processing power. So they use the desktops, the personal computers, kind of improvement of personal computers from the 70s. And the 70s, that's when first personal computers came along, And that's what we have at the moment, like a much improved version of them on your laptop. That's more or less a microcomputer. But in the older days, it had very little power, processing power, little memory and all that. I remember buying one of them. They're useless. Obviously compared to what we have now. Advances in computers technology, the major changes in size. Computers are getting smaller, and that's transistors. The really main advantage or development was transistors that reduced everything. They consume less power, and they're getting cheaper, and they deliver more processing power. They're faster today than any other time before, and we have more memory and bigger storage capacity. Things have been improving. There's a law. Somebody called Mr. Moore. He made a statement. I think he used to be in IBM or so. He said, every 18 months, you need to know this law. Every 18 months, the power of computer and capacity doubles. Doubles every 18 months. This is known as Moore's law. And ever since the 60s till now, it's found to be true, and it's still true. Every 18 months, the power of computing increases. Sometimes more in memory, sometimes more in storage capacity, sometimes in processing power, but there's always an improvement of doubling in power every 18 months. Maybe we might be reaching towards the end, and we have to kind of invent something new to start to keep on this. But every 10 years or so, there's change in technologies, whether in storage technologies, like from tapes to hard disks to optical disks to whatever the next one, the next storage is. Non-movable kind of storage devices. And we will look at storage devices later on during, towards the end of this course, we'll do devices. Operating systems, these are some of the famous operating systems that were used. Microcomputers, these are computers like the laptops and the desktops and all that. Linux, Macintosh, if they're made by Apple. MS-DOS, that was the single user one, and then Windows, and Windows just kept on developing. Many computers, they use Linux or Unix, IBM. So these are, as you can see, Unix and its smaller version of Linux are the development. IBM had its own operating system as well that was developing over the years, and Microsoft Windows. So Unix started as an old one and then changed into Linux, as you can see. And there are many different types of operating systems, but not a lot, as you can see, they're quite limited. There's Unix and its versions of Linux. There's Microsoft DOS, and it's transferred into Windows. And a few other systems that didn't survive or changed. So now, types of operating systems, not computers. Types of computers, remember the computers. There's mainframe, mini computer, microcomputer, and supercomputer.
Quantum computer.
One laptop.
Quantum computer.
Okay. I didn't quite hear, but okay, my question is, which one is more expensive? Or which one is more powerful? The mini computer or the microcomputer? My question is clear. Mini computer or microcomputer? Kamush, mini computer or microcomputer? Micro. Which one is more powerful? Microcomputer. Do you agree with him?
No. I think it's that.
No, this time it's clear. Which one is more expensive? Mini computer or a microcomputer? Mini computer. The mini computer is like the mainframe, but reduced, but still powerful. How many users would a microcomputer use? 1 or 20? What about the mini computer? Approximately, yeah. What about the mainframe? How many users, approximately? Let me give you numbers. 1 or 20 or 200. Which one would be closer to a mainframe? 200, yeah. Mainframe computer has many users. Multi-user computer. A microcomputer is a single-user computer. You need to remember these things. I keep throwing these questions at you until you know the difference between a mini computer, a microcomputer, and a mainframe computer. Which one is the more expensive, a mainframe or a microcomputer? Mainframe. Okay. How much does a microcomputer cost? Excuse me? Are you with us? Good. Do you know how much a microcomputer costs approximately? $1 million, or 200,000, or $1,000? A microcomputer. Yeah, 1,000. This was back in the 70s, give or take, of course, these prices. But you need to know which one is more expensive than the other. You don't need to know the exact figures. But don't tell me that a microcomputer that's for a single user costs more than a mainframe. Mainframe is the most expensive computer. Okay, so now all these, they need operating systems. So let's look at operating system. What are the different types of operating systems? First operating system was called the batch. Not first, this is one way of processing in operating systems. A technique called the batch operating systems. Batch processing, not batch operating system, batch processing. Batch processing means you take a group of functions or jobs in a batch. That's why they call them batch. That means you take a few of them. You don't run them one at a time. You take a group and run them together. Why? Because, for example, in the old days, this is the way things worked on main computers, by the way, that powerful computer. That's the way I worked when I started. Like, I used to write a program. Nowadays, you write a program and you say run, you execute it on your machine, and you get the results immediately. There's an error on line 15, line 20, line 27. You probably have 200 errors, right? You get that in 1 second. In the old days, when I used to go to college, and we write a program, the operating system was not as good as what we have now, nor the machines. So there was only one CPU. So, and we were sitting at a terminal that had no memory, no CPU, no memory, nothing. So every time you write a command, it goes to the main memory. So anyway, we say, can you execute this program for me? So our request goes to the operating system. It gets in a list. And then an individual comes in, person, operator, that comes in and say, oh, I have 200 programs to run, right? There wasn't an automation. And, for example, we had different languages, like, I don't know, what language do you use now? Java. Then there was a language called COBOL and Pascal and C and so many. So different programmers are writing, one is writing in Pascal, one in C, and every one of these you need a compiler, the translator that translates your English code from Pascal or Java into a machine code. So this guy had to first upload the compiler. And in the old days, again, there were no hard disks, so the compiler is on a tape out there, so I had to go and get the tape, and they say mount it onto the reader, onto the tape drive. It takes a few seconds or minutes. You have to put in the tape that has a reel, not just a cartridge, not even a cartridge as we have now, a tape, you put it in. No, a big reel, you put it in, and you pull the start of it, go through all the heads, and go around, rotate it around the other reel. They say, right, that's now read the Pascal compiler. So the Pascal compiler is read. Now read this user's program, again on a tape, and execute it. Now the next job, the next student is COBOL compiler, a different compiler. It's not on this tape. We have to take this tape off, go bring the other tape in. So what they say, hold on, and then the next one is Pascal. So you have to bring back the Pascal. That's why I said, no, it's your batching. So before they start executing, they look at all the programs that need Pascal, they put them together, and all the programs that need COBOL language or compiler, put them together, Doesn't matter, you could have just submitted your job, you happen to be, with the same group. Now, we take all the Pascal, let's run the Pascals first. Upload the Pascal compiler once, run all the Pascal programs, and they all produce results and they're stored in memory or somewhere, and then we take it down, then we bring the COBOL compiler. So it's a matter of improving performance for the user, for the operator, to only upload the required application or program or compiler once and do all the jobs that need this program. When you finish with it, you take them all out, bring another group, and they call this batching. So a batch job, it has features. It's a job that takes a long time to respond back to you. You don't get your response immediately. You don't run the program and get the result in a second or two or a minute. It might take an hour or two or a day. Because we're not going to run it now. We're going to put it in a group, in a batch, until we have enough to run them, for example, right? So that's the first disadvantage of batch operations, is that they take a long time to respond. So response time is very long. So if you're doing a life depending on, operation, or flying an airplane remotely, from a pilot sitting here flying an airplane, that batch doesn't work. Because every time you say, move the stick up, it might take minutes or hours before you actually execute that instruction. So batch operation is not done for any urgent jobs. It's not useful. It's not good for any urgent jobs. It's only good for jobs that don't mind waiting for a long time. And we call that response time. So if you don't care about response time, batch jobs are good. When are they used nowadays? Nowadays, batch jobs are used like backup operations at night. Most companies, most organizations, they do their backup at night. Now they're changing, and some of them are doing their backups on the spot. Live backup, duplicate kind of mirroring, they call it. But still, many companies, though, they don't do that. When they shut down, all banks, when they close at 5 o'clock, they start doing all the backup operations. Backup is just copying your files, making another copy, just in case the place goes on fire and we lose the information. We have another copy, maybe in another building. They call this backup operation. Or a virus hits your machine, at least you have the data. Or staff member goes mad and deletes the important files. For some reason, we have another backup. So backup is like a batch operation. Why? Because you don't need to do it now. You can do it later on at night. You can run all night. When it's finished in the morning, we don't need really a quick response. Right? Batch jobs are cheap jobs that you don't need quick response for them. So that's one way of processing. In the old days, it started because we had to do everything manually. We had to, this is the best way to organize it. But then it continued. Even after automation, we still kept some jobs that are okay to do in batches. And usually priority jobs. So high important priority jobs, we do them first. The low priority jobs, usually they end up being done later, like batch jobs. The next system is called interactive processing. Interactive processing is a system that requires a quick response. Like nowadays, almost everybody uses interactive systems. Like you go into your computer and you type griffithcollege.ie. That message goes to the server, and the server sends you back the main page. You expect that response. Maybe, I don't know, how long does it take to get the main page? A second, 2 seconds, 3 seconds. Maybe 5 seconds. If it takes 10 seconds, you probably say, what's wrong with it? There's no, it's dead or something, or down, or if it goes minutes, forget it. So that's what we call interactive jobs. The jobs that require quick response time. That the word response time now is important from now on. Remember, we had turnaround time as a term we used before. The time from you put a request until the full request response is finished. That's called turnaround time. What's response time? Response time from the moment you put a request, you hit enter, until you can see something is happening. That means, hey, there is a response. The program is not dead or the line is not down or anything. Imagine if I say, print on the screen the list of all the students' names, for example, or all the list of the names of all the books in the library. From the moment you hit enter, you start seeing the lists appear and appearing. Might take a minute to finish the whole lot. Finish the last name, that means that's turnaround time. The turnaround time from the moment you put the request until the end of the execution. We know that, that's turnaround time. What's response time for this program? Response time from the moment you say print the list, you hit that command, and you see the first name. You got the response. That's called response time, okay? So response time from the moment you ask for something until you see the first sign of reply of a result. That's called response time. Response time needs to be fast with interactive systems. So interactive systems require short response time. And these response time and turnaround time, these are going to be the measures that we will be using right through performance of, during this semester. So there are a few things that we use them as measurements in comparing two techniques. Will we use this technique with this technique? How do we know which one is better? Which one has quicker response time? Or quicker average response time, or average turnaround time. So anyway, so if you're asked what's the difference between batch systems and interactive systems, what would you tell me? Say again? Batch is used for backup. No, okay, I didn't say what is it used for. So what's the difference between these two processing?
It's less response time.
So batch system takes less, it gives shorter response time. And interactive?
It gives a little fast response time compared to that.
Longer or faster or shorter response time? Shorter. So batch systems have very long response time. Interactive have very short response time. Okay. Are you with me, guys? Right. Now, let's look at the next system, real time. What's real time? Just from the world, real time. What does that mean? Does that have short or long response time? Short response time. So, interactive also has short response time. So these two systems, they both have, it's a requirement that they must have, or they should have short response time. So what's the difference between them? Real time is something that you run on real life. That is, like the example I gave of flying an airplane, real airplane, but the pilot is not sitting in the plane. All the passengers are there, but the pilot is sitting at home and flying the airplane. And if the airplane is coming down, well, there's a mountain there, you say, okay, pull up. And when the pilot pulls up the stick at home, the response should be immediate. If the response is not immediate, the airplane will crash. That's when we say we need a real time. A real time, there's no option for failure. There's no option for delay. Interactive is always nice. It's good to have short time. But occasionally, we may not have a short, it might be a little bit delayed. But real time, the system must be responsive, 100% responsive, 100% of the time. For real time, there's no messing. So the requirement is even stronger in real time than of short time. Short response time, 100% of the time. It has to be 100% responsive. That's the difference between interactive and real time. They both might have short time, but with the interactive, we can put up with a little bit of a delay sometimes. It may not work 100%. So anything that cannot accept any delay, don't use. Interactive systems use real-time processing systems. And it's important for those. Hybrid system. Yeah, so companies, they might have a combination of two or those three. For example, a company, maybe game playing. You know the games? You might be playing games. That needs a quick response all the time. Maybe interactive system. It's not really life dependent, but it would be great to have real time, but not necessarily. But maybe at night they might do batch processing and they back up all the results they have today and who are the first winners and all that. Sometimes there are places where you can have a doctor operating on a patient in another country. You over the internet, and the doctor is, say, in America, and the patient is in, I don't know, South Africa or the Philippines or somewhere, and they have a robot, you know, knives and things like that, and the doctor can move them. So, you know, and if the patient starts bleeding, the doctors say, okay, go grab and stop that bleeding. You don't want any delay here. When you delay, the patient will die. So you need real-time system for those. So that's when you decide. You go to work in a company and they say, hey, should we go for interactive or real-time system? You decide. You have to say, okay, what nature, what kind of nature of work? What happens if there's a bit of a delay? Is it going to cause a chaos? Is it going to cause calamity? Death or something like that? No, they say no. If there's a delay, it's okay. Oh, well then, don't go for real time, go for interactive. Because the commitment, the cost is going to be huge between those two. It's like another thing, a bank that says, we run our systems 24/7. Imagine if a company says 24/7, that means if their machine, what happens if their server breaks down? And you know, they have to bring another server. They have to, that takes hours maybe, or minutes. That's not 24/7. You can sue them for that time. If a company says 24/7, watch them. They must have some live backup. At the moment this server dies, another one comes in operation immediately. And that's very costly. It's not cheap. So the requirements are different anyway. So interactive and real time, this one, everything has to work. The system has to be 100% responsive. Always, response is always there and good and short, 100% of the time. Always responsive. That's the major difference between it and interactive. Interactive has a short response time, but sometimes it might not be short. Okay, so this is the stuff you can read. I've just talked about it. These are some of the handheld devices. This is an ancient handheld device. Hybrid systems, embedded system. Well, what's an embedded system? It's an operating system, but operating systems are normally computers. No, if we have a device that's not a computer, like a washing machine. A washing machine has a CPU, processor, and some memory, and it does certain jobs, specific jobs. That's called a hybrid. It needs an operating system, but not the full operating system we have on computers, but a small operating system. So lifts, you know, the lifts that bring you up and down, escalators or something like that, they might have electronic CPU and maybe a small operating system. They call these embedded systems. So an embedded system is an operating system that's not on a computer, on a device that's not a computing device. Though it might have its own CPU and so on. So read these notes here. There's a bit of historic when how computers started, what they looked like, and that's what computers look like. That's the whole thing that you see in that room. You probably have it in your laptop now. That's how much they've evolved, and that's at that time it was real, the state of the art, the best that's there, the smallest, the most efficient. But as you can see, that's probably a card reader, or this one is a card reader. We don't even use card readers no more, or keyboards or scanners. So this tells you, it gives you a bit of history. Nice to read it. It gives you just an overall picture, nice afternoon read. But then in the 70s, they developed into these. These are probably tape drives and hard disks. In the 90s, things got better. Let me go to threads. What's a thread? We'll talk about it again, but just for now. But first, what's a process? Imagine this is the computer. The computer is just lots of millions and millions of switches. And every 8 of those switches get together and we call them, what do we call 8 switches? A byte, a byte. Okay, if you haven't done, you will learn the byte and so every 8 switches are called a byte and we give them a number, 0. Byte number 0, byte number 1, 2, 3, all the way to the millions of bytes and billions of bytes that we have in memory. And when you start running the operating system, it's going to be our story for the next 2 weeks. The top part, say from 0 to maybe, let's just for argument's sake, say 20,000, this belongs to the operating system. So the operating system has a mark here, 20,000. Everything less than 20,000, it all belongs to the operating system. All the operating system programs go in there. Not all the operating system, but the essential part of the operating system, and they call it the kernel. So what is, if you're asked what's the kernel, it's the essential necessary parts of the operating system. It's always in memory. If the computer is switched on and running, then the kernel is there. There are parts that are not usable a lot, so they're not on main memory, they're on the hard disk. For example, somebody says, format a hard disk. You don't do that every day. You probably do it once a year or once every 5 years. So you need that function. We don't keep it in main memory. Main memory is so important for continuous use. So we have that function on a hard disk. We go bring it up for a short period of time, format the hard disk, and then get rid of it. That's also part of the operating system, but it's not part of kernel. So what's a kernel of an operating system? What's a kernel?
Part of operating system.
Yeah, which part? A kernel. The most essential part of the operating system, the most important part, the minimum operating system you must have, we call it kernel. And it's always sitting in the main memory. It's called kernel, so I didn't see it there. Okay, now a program comes in and say I want to be executed. The program manager, the operating system calls the memory manager and says, hey, we need some memory. So they're given memory. Here it is. This is program number 1. It's running from memory, say 20,000 to, for example, 40,000. Right? And here's all your code. And also, as well as code, they give you in memory manager, they give you a space called the data. Data means X, Y, any variables you use, they're there. They're your variables. They're little storage space for you. As well as your code, you give a space called the data. So anytime a program is loaded to memory, there's the code segment, the code part, the data part, and then we have a tiny bit small part we call the stack part for this program. So all information belonging to that program. Another program comes in, we give it another space. So here's program number 2, has its own space of memory. And the memory manager knows program number 2 starts from location 40,001 to say 60,000. Just relax and enjoy it. You don't have to write. We'll go through this in more details. I just want you to know the idea, how things work. Now, if the operating system, if this guy says, change my X, I want to put value X, put 3 in it, or something like that. That's okay, that's legal, because this part belongs to this program. But the memory manager will run a quick test first, because in reality, when you translate this, there will always be an address. This is like the executor of the CPU needs to know, where will I write the 3? It will say the address, for example, 30,312, so somewhere here. So the memory manager will say, oh, the address 30,312, does it fall between 2,000 and 40,000 or 20,000? If it does, then yeah, it belongs to this program. And if it doesn't, then it will terminate the program. So if this second program here, if this program says change this location of memory, the memory manager will terminate it immediately. Will say, you're not allowed to write in that area. That area belongs to a different program, program 1 or process 1. Like I was saying, program. But for now, I'm saying program and process interchangeably, but in the future, they are, once they're sitting here, they are processes. So process one is only allowed to change memory in its own space, if it doesn't. Now, how many programs or processes can we execute? It depends on how big the memory is and how big each program is. Let's say we get program number 3, it's really big. Program 4 is about this much. Program 5, program 6 is also another large program. And this is space free still. So now we're executing 6 programs. And the CPU will go to each program. Well, we know it doesn't go, but CPU is sitting there executing. But now we're running this. We're sending instruction from this program to the CPU. When this one says, I need input, say, okay, go to sleep. We go to the next program. Take instructions and send it out to the CPU. Now, there's another way of executing. So in this way, you can only run 6 programs. And these processes cannot talk to one another while executing. There's no way for this process to talk to that process. This one has its own variables, just like this one, and that one has its own variables. The only way they can communicate is if this one, say, write to a file, which is a very slow operation, and close the file, and this one opens the same file. Okay, but that takes seconds or minutes before execution can happen. It doesn't happen in microseconds or milliseconds or millionth of a second. But there's another way of executing program. We can take another, say, for example, here's memory, and this part belongs to the operating system. And let's say this part here is now process 1. So process 1 has memory space from this location to that location. Now, there's a new way of programming, and it's called processing. So processing is using something called thread. So threading or thread is like a second program that runs. But you see, the instructions for the programs are here. And there's somebody executing, and maybe they start executing, they get to line 200 in that program. So there's an executor, there's a program being running. Now, we might say, create another image of this code, but don't write another space. Remember, every time you put a program in memory, you need space in it. No, we say, let's use the same program, the same space. But now we have a second executor. So this is, let's just say now we call it S1, and this one we call it S2. So there are 2 processes running, executing the same code on the same space of memory. So this saves us, we can actually run 5 of these, but they're running the same program. But there are 5 separate implementations. It's like having a chef to cook something, walks into a kitchen and starts preparing this recipe. But then now we introduce another chef, we say, go follow the same recipe. So they start again, maybe 5 minutes later. When that guy had chopped all the onions and the meat, this one is just now starting to chop the onions. But we have 2 separate entities following the same code. This is what threads are like. So threads are different processes that are executing, but they're all executing the same code. What's the advantage of this? It's a little bit more complicated, right? Because now instead of just one execution here for 6 and 1 execution for 4, this program, now we have the same program, we might have 3 or 4 executors running the same thing. The advantage, we are saving memory, first thing. Instead of you running a program, when your friend comes and runs the same program, if you double click that icon, your program code will be given there. If your friend separately clicks the same icon, they'll be given the same code, but they'll be put in different part of memory. But this is another way of doing it. We say, many people can run it, but we'll run the same code. This is called threading. This is a new, well, not new, but it's a later way. It's an improvement way. If you want to execute the same program, sometimes, of course, you don't want to execute the same program. But threading is important because you can say, listen, if you are user number 1, you can execute this part. If not, you can go and execute. So you can have actually different executors executing different parts if you want, based on their ID. But anyway, the advantage of this is that you you're running many programs, but in the same memory space. So you're saving a lot of memory space. The other good thing is that now each one of those executors will have the same access to the same code. So they all can see the same X and Y. So they can communicate through those. So if this guy puts value 0 in X, this guy can see it. They might use it to indicate something. Or we might have an array here. This guy puts information in the array, and this guy takes information from the array. So they can communicate together. This is the good thing about threads. In thread programming, you save memory, but you also, the processes, this is the only way processes can communicate directly to one another. Two running programs, normally, they will never, ever communicate. They're not allowed to communicate on computers. Separate programs, they will never communicate directly while they're running. But unless if we do the threading bit. And why? Because they both have access to the same variable. See this data area, this belongs to this program. This data area belongs to this. They never kind of mix. While now, there's only one data area, but it belongs to all those threads. So threads can actually talk together, communicate together. So that was the point I was trying to make. Let's go back and, right, so I'm going to stop this now for a second. Okay, quick questions. Which one is more expensive, a mainframe or a mini frame or a mini computer? A mainframe. And which one? Which has more users, a microcomputer or a mini computer? A microcomputer. A mini. A microcomputer is like a personal computer, like your laptop, one user. Okay, and which one has shorter response time? A batch processing or what's that? Interactive processing. Interactive processing. What's a Kamush, guys? Please. What is the real-time processing? How do you define it? Yeah, go on. Okay. Yeah, I can't afford delay. Give me another definition of, another understanding of real-time operating systems of processing.
The response time is immediate.
Pardon?
The response time is immediate.
Yeah, well, interactive systems also expect response time immediate. What about real-time systems?
It's quick response, but without delay.
Interactive also ideally would have quick response without delay. What's real-time systems? Pardon? What?
Really quickly, shorter.
Yeah, okay, so is interactive systems. What's real time? What's the difference between real time and what makes real time different to interactive systems?
Shorter.
Yeah? Real time. Kamush, guys, please. Yo. Say again, sorry. Okay, it's response immediately. So is interactive system. Okay. I'm not saying it's wrong, I'm just saying, okay, I want to hear something different definition. Go on. 100% responsive, 100% of the time. That's real time. Interactive system is responsive. 100% responsive, but not necessarily 100% of the time. Sometimes it may not respond 100%. Okay, but so be careful. Just the difference. Sometimes the differences are minute, but they're important. Which one is better, to run 5 programs as 5 processes or 5 threads? Which one is better, running 5 processes or 5 threads? Processes. Why? That's the question. Why? Yeah, but some of the processes, here they are, 1, 2, 3, 6 processes running simultaneously. We can have 6 threads running simultaneously. Which one is better? Why?
Because you located with memories and you can share the
Yeah, because we can save memory if we run threads. Any other reason? Threads are better than processes? They can communicate together. If they were threads, they can communicate together directly. If they are processes, they cannot, not on memory. That could, use files or something that's real slow. Guys, I'll ask these questions. Please look at the notes. And if you have a problem with attendance or, yesterday's attendance or now or you cannot attend, I need your list of names and for today's date. So hopefully whenever you're sorted out, we can have to include it. Okay, thank you very much. I'll see you.